this lesson, we're looking at enthalpy and calorimetry examples. So this will be a little review where we are looking at the first law of thermodynamics, defining enthalpy, explain its classification as a state function, writing and balancing thermochemical equations. We did a little bit of that this last lesson. Calculate enthalpy changes for various chemical reactions. And we're going to start looking at Hess's law. So again, thermochemistry is a branch of chemical thermodynamics, the science that deals with the relationships between heat, work, and other forms of energy. Substances act as reservoirs of energy, meaning energy can be added to them or removed from them. So remember, when bonds are breaking or bonds are forming. Energy is stored in a substance when the kinetic energy of its atoms or molecules is raised. So the enthalpy of the system is the sum of the internal energy of the system and the product of pressure and volume. Enthalpy change is the heat evolved in a reaction at constant pressure. So again, when the bonds are breaking or forming, it's either an exothermic reaction or an endothermic reaction. And an exothermic reaction is when we have heat loss. So my delta H is negative. Endothermic is when we have bonds forming and my delta H is positive. When heat is released by the system, again, my delta H is negative, and that is an exothermic reaction. When the delta H is positive, the heat is being absorbed by the system, and that is an endothermic reaction. Some examples of that is when here we can see the system is losing heat to the surroundings. We can see that it is leaving the system to the surroundings. That is our exothermic. And we can see when the surroundings are giving heat to the system, so the system is absorbing the heat, that's our endothermic. Our chemical heat packs is an example of an exothermic reaction, and a cold pack that contains ammonium nitrate is an endothermic reaction. Here's a molecular view of exothermic reactions. Again, the surroundings temperature rises due to that thermal energy that's being released. That extra thermal energy comes from the conversion of some of that chemical potential energy in the reactants into kinetic energy, forming those products, and that is released in the form of heat. That happens when old bonds are broken, new bonds are made. And the products of that reaction have less chemical potential energy than the reactants. Remember, an exothermic reaction, my reactants have high energy and my products have a lot lower energy. It gave off heat. That difference from where I started to where I finished gave off heat. That's a negative delta H. The enthalpy change is an extensive property. The more reactants you use, the larger the enthalpy change. So we can calculate enthalpy change for the number of moles of reactants like this. This is the combustion of propane. We have C3H8, which is propane, like what you would use in a gas grill, or what you would use, some people use it to heat their homes. And so here is my full thermochemical equation that's balanced. And we can see that for every 1 mole of propane, we can see that 2,044 kilojoules of heat energy is released. So this is we could write this as a proportion, as a stoichiometric ratio. We also could say, so that's for propane, we could also say that 5 moles of oxygen being combusted produces 2,044 kilojoules of heat. So that can be its own ratio. We could also say the same thing for carbon dioxide gas. For every 3 moles, this is how much heat is produced. For every 4 moles of water, and so on. So let's do an example problem here. Let's look at this problem. We want to know how much heat is evolved in the complete combustion of 13.2 kilograms of propane. So if I'm given kilograms, first thing I want to do is get to grams. And we know that there's 1,000 grams in 1 kilogram. So 13.2 kilograms is equal to 13,200 grams of C3H8. Okay, so you see what I did with that. If you want to see the 13.2 kilograms, what do I want? Grams. What have I got? Kilograms. 1 kilogram is 1,000 grams. So my units will cancel. So 13.2 times 1,000 gave me my 13,200 grams. Okay, so this is my starting, because we know that in chemistry, if I have grams, grams can get me to moles, right? So what do I want? I want moles of propane, C3H8. What have I got? I've got grams of propane. Oh, that's an 8. Now, I need to look at that grams to mole ratio. So for every 1 mole, I need to add up 3 carbons, so 12 times 3, and then 8 hydrogens. Each hydrogen is 1 times 8, so I got 36 plus 8. So I should have 44 is my molar mass of propane. All right. That gets me to moles of propane. Now I can look at my balanced thermochemical equation, and I can see that for every 1 mole of propane, my delta H is negative 2,044 kilojoules. So what do I want? I want kilojoules. What have I got? I've got moles of propane. And I know my ratio is 1 mole of that for every negative 2,044 kilojoules of heat. So now I just need to do the math. I need to do 13,200 times 1 times negative 2,044, all divided by 44. And let's plug it into our calculator. And I got negative 613,200 kilojoules. And this tells me that that negative, it's an exothermic reaction. How do you feel about that one? Hopefully you got the same answer. Let's look at another similar problem. We want to look at how much heat is evolved when a 0.486 gram diamond is burned. Well, diamond in its pure form is simply carbon. And when we are combusting, we are applying oxygen to it. So these combine to simply form CO2. And it tells us the enthalpy of combustion for carbon, for the diamond, is negative 395.4 kilojoules for every mole of carbon. All right. So if we're starting with 0.486 grams of my diamond, which is carbon, if ever I'm given grams, I need to go to moles. So what do I want? Moles of carbon. What have I got? Grams of carbon. I know that for every 1 mole of carbon is 12 grams. That's its molar mass. I would find that by looking at the periodic table. And then, so that gets rid of my grams of carbon. Then I can go from moles of carbon to kilojoules by using my enthalpy of combustion. So I know that it's negative 395.4 kilojoules for every 1 mole of carbon. Again, I know that that 1 mole of carbon is because of that balanced equation. So now I just need to multiply across and divide by 12. And my calculator should get me negative 15.9 kilojoules. This also tells me that negative tells me that it's an exothermic reaction. That means that it is heat is evolved, heat is being emitted. That means exothermic. To measure delta H, we use calorimetry at a constant pressure. The reactions that are done in aqueous solutions are at constant pressure. And we use a calorimeter that's nested in between, kind of like this, 2 nested foam cups that contain the reactants in the solution, and we cover it, and then there's this thermometer that is inside of there, so we're able to kind of maintain the system so it's not just open to out in the air. Remember that the heat of the reaction is equal to the opposite. So the heat given off is equal to the heat absorbed. And remember, Q is equal to M times C times delta T. So the delta H, the enthalpy of the reaction, is equal to Q at constant pressure, which is equal to Q of the reaction. And then to get that delta H, the reaction per mole, we would divide it by the number of moles. Let's look at an example problem. Let's look at this problem. What is the delta H for the reaction per mole of magnesium? For the reaction, magnesium added with HCl creates magnesium chloride and hydrogen gas. If 0.158 grams of magnesium reacts in 100 milliliters of solution and changes the temperature from 25.6 to 32.8 degrees Celsius. Well, I see that and I immediately think, oh, well, that's my change in temperature. So let's first look at the, find the Q. We know that Q is equal to M times C times delta T. So let's look at the solution. And the mass, we know if we have, it doesn't tell us it's water, but we're going to assume, since it doesn't say, that it's a solution of water, H2O. If we have 100 milliliters, we know that the density of water is 1. So if we have 100 milliliters, that's equal to 100 grams of water. So my mass that I'm going to write down here is 100 grams for my mass. We also know, if we look back, way back to this, my specific heat, that water specific heat is 4.18. So we're going to use that for my specific heat, 4.18 joules per grams degrees Celsius. And then for my change in temperature, we're going to find that difference and do 32.8 minus 25.6 to get 7.2 degrees Celsius for my change in temperature. So let's do that math and see what we get as far as joules of heat. So we got 100 times 4.18 times 7.2. Okay, and we get for this reaction 3,009.6 joules of heat. Now, we know that to find the delta H, that is usually in the form of kilojoules per mole, right? And that's what it's telling us. We need that for every mole of magnesium. While we're given joules, let's quickly change that to kilojoules. Remember, there's 1,000 joules in a kilojoule, so all we need to do is move our decimal point over 3 spots or divide by 1,000. So I'm going to make this 3.0096 kilojoules because we're going to end up going to kilojoules here in just a minute. Okay, now, so we've got the kilojoules. Now we need the mole part. So we're given grams of magnesium. And we know that if we're given grams, we can get to moles, right? So we're going to just go 0.158 grams of magnesium. And we're just going to look at the periodic table and look up magnesium's molar mass. And we will see that for every 1 mole of magnesium, that there is 24.3 grams of magnesium. That's its molar mass. So when I do that math, I'm going to get 0.0065 moles of magnesium. All right, now I just need to put these two together because my delta H for the reaction for every mole of magnesium is my Q, my 3.0096 kilojoules divided by my answer, 0.0065 moles of magnesium. So let's plug that in. 3.0096 divided by 0.0065. And we get 463.01, so we're just going to leave it 463 kilojoules per mole. There we go. So when we look at this, just to make sure everything looks right, when we place this 0.158 grams of magnesium into solution, it absorbed heat. The solution absorbed heat. This is a positive 3,000 joules or 3.0096 kilojoules, which means that if this is absorbing the heat, then this must be releasing heat. So this delta H, we need to show with a negative sign that it is releasing heat. So if the water is absorbing that energy, that means that the reaction, the magnesium that was placed in it, was releasing that heat. So just to make sure that we were hearing that and seeing that, I got to show that this is a positive, so this must be a negative. Let's look at another practice problem. We want to find the final temperature of a solution in a coffee cup calorimeter if we have 50 milliliters of HCl, so I'm going to write down HCl, added to 50 milliliters of NaOH, and underneath of these, I'm just going to write down that I have 50 milliliters of that, 50 milliliters of that, and we know that this is a compound, so it's going to be a double displacement reaction. So my products will be H2O, HOH is H2O, and NaCl. Oh, hold on, I have low battery. There we go. So I've got HCl plus NaOH to give me water and NaCl. It tells me that the delta H of the reaction is negative 57.2 kilojoules per 1 mole of NaOH. Okay, so we want to find the final temperature. Well, final temperature is going to come by doing the m times c times delta T. Okay, but before we get there, we need to figure out, well, my heat of this reaction is for 1 mole of NaOH, but this, I don't think we actually used 1 mole of NaOH for this reaction, so we need to double check this. So we use 50 milliliters of each of these reactants. It does tell us that each of these reactants is 0.250 molar. So I'm going to write that right here. They have a concentration of 250 m, and this one is 0.250 m. So we know volume and we know concentration. So do you remember back when we could calculate, if I know to find that concentration is moles divided by liters, right? Moles divided by liters to get concentration. So if I know concentration in liters, I can multiply concentration in liters to get moles. All right, well, this has to be in liters. So let's make 50 milliliters is equal to I'm going to go back 3 spots, 0.05 liters for both of those. So I'm going to do, to find moles, I'm going to do 0.05 liters times 0.250 molarity to get 0.05 times 0.250 to get 0.0125 moles of NaOH, and 0.0125 moles of HCl was also used. So we did not use 1 mole. We used that much. So let's figure out the Q, how much heat this reaction actually used. So we're going to take this. Remember, it told us negative 57.2 kilojoules for 1 mole? Well, we didn't actually use 1 mole, so we're going to take this and multiply by 0.0125 moles, so that moles and moles will cancel out. And that will give us 57.2 times 0.0125, 0.715 kilojoules. Now, remember when we would do Q equals m times C times delta T, and Q is in joules. Because this is in kilojoules, let's change it to joules. So we're just going to go times it by 1,000, 715 joules. Now, let's do m times C times delta T. Use a different color here. So if I know that my Q, the heat given off in this reaction, is negative, right? That negative tells me that it's exothermic. That means that this reaction, this NaOH, it is releasing energy. The solution, the water, is absorbing the energy. So I'm going to have a positive Q over here, 715 joules of heat. I'm also going to say that this solution that's absorbing it is 50 milliliters and 50 milliliters for 100 milliliters of that solution. It also says to assume the density of the solution is 1 gram per milliliter, just like water. So if it's 1 gram per milliliter, if I have 100 milliliters, I also have 100 grams. So that is what I'm going to use for my mass. 100 grams. And for C, the specific heat, we're going to use the specific heat of water, 4.18. It actually even says the specific heat of the solution is 4.18. And my change in temperature, I have to find my final temperature, so TF minus, it tells me the initial temperature was, what does it say? Initial temperature was 19.5 degrees Celsius. So let's do some simplifying. 100 times 4.18 would be 418, right? Minus 19.5 equal to 715. So now let's divide both sides by 418. And that'll give us 715 divided by 418, 1.71 equals TF minus 19.5. So to find my final temperature, I'm going to add 19.5 to both sides. So 1.71 plus 19.5, I should have 21.21 degrees Celsius. Let's see if this makes sense. I have a reaction that is exothermic. It's negative 57.2 kilojoules per mole. Now, that was for 1 mole, but we didn't quite use a mole. We found by using our molarity equation that we actually only used 0.0125 moles. So we just got rid of the moles to find out how much energy we actually used, how much heat was actually produced. So we know it's an exothermic reaction, it's giving off heat. We then took that Q and plugged it into our Q equals M times C times delta T. The mass, we added up our 2 reactants, 50 and 50, to get 100 grams. We used the specific heat given to us, and we did delta T for TF minus TI. We knew the initial temperature. Our initial temperature was 19.5, and it raised very little to 21, which makes sense because if it's an exothermic reaction, our initial temperature being 19.5, it's going to raise a little bit, but remember, it takes a lot of energy to raise the temperature of water. So we went from 19.5 to 21.21. Pretty good. I mean, it took a lot of energy to raise it just that, not even 2 degrees. So, good job. Let's look at another example problem, and this is going to be similar to a lab that you are going to do with your lab kit. So we have 55 grams of iron that's at 99.8 degrees Celsius. We can even see right here, we have this hot metal. I believe you are going to use copper pennies. So we're just going to say we have this hot metal or your hot pennies, whatever your hot thing is. We have, it's at 99.8 degrees. So I'm going to make a little list over here. We're going to have our metal, and we are told its mass, which is 55.0 grams. We are told its initial temperature, 99.8 degrees Celsius. And then we're told that it's placed into 225 grams of water that's initially at 21 degrees Celsius. So let's put down our water. Its mass is 225 grams, and its initial temperature is 21 degrees Celsius. So we have hot metal, we have cold water. I believe you are using 100 grams that you're going to be measuring with your graduated cylinder. So at thermal equilibrium, the water and the iron are both at 23.1 degrees. So what we're going to do is we have our metal, hot metal, cold water, and then we are going to make this system where we put the hot metal into the cold water. And it tells us that the final temperature for both is 23.1 degrees Celsius. Okay, so the metal cools in the exothermic process. So the change in temperature of the metal is negative, because if I look at that metal, my final temperature minus my initial temperature, so if I did 23 minus 99, right, that would give me a negative. Its temperature is going down, so that is negative. So when I look at calculating my Q, my heat, okay, remember Q is M times C times delta T. If I have a positive mass, I have a positive specific heat, but I have a negative change in temperature. That's going to give me a negative Q, right? So that Q is negative, exothermic. The water is warming up though, so it's an endothermic process. The change in temperature of water is positive. If I look at this, my final temperature is 23, but I started at 21. So my change in temperature is a positive number. So positive times positive times positive. My change in temperature is positive. My Q is positive. And that would make sense if you think. Remember us learning that the Q of, let's say, my metal has to be equal and opposite to the Q of my water. Okay, there is one more piece of information that we know. It's asking us to find the specific heat capacity of the metal. So we need to find C, a specific heat of the metal. I know specific heat of water. Remember when we look back at our specific heat capacities? Water is always a constant at 4.18. You can leave it at 4.18. Some references will tell you that it's 4.184 joules per gram degrees Celsius. So either way, it's a thousandth of a position. So some tell you 4.18, some tell you 4.184. So let's look at this. We know that, like we said, our Q's need to equal for whatever we lost for the metal. So the Q metal, which is what the heat that was lost, needs to equal the Q of the water that was gained. So since we know all of these variables, let's find the Q of the water. That is our endothermic process. So let's do our mass, our 225 grams times our specific heat, 4.184 joules per gram degrees Celsius. And our change in temperature, let's do 23.1 minus 21. I should know that this was 2.1. So this is for our water. And let's plug it into our calculator. So I'm going to do that 2.1 times 4.184 times 225 grams. And I get a Q of 1976.94 joules. This is joules of heat absorbed. Okay, that's good. Step one is solving for the heat gained in water. Let's write that down. Step one. So now let's think what we need to do for step 2. We need to use this Q that we just solved for to solve for the specific heat of the metal. So we're going to use the Q found from water that was absorbed to solve for the specific heat, or C, for the metal, because that will then be our only unknown variable. So let's look at plugging that into this equation. So we are going to do M times C times delta T again. We know our Q that we just found right up here. So we're going to use this 1976.94 joules. We know the mass of our metal, I'm going to pull this down, is 55.0 grams. We don't know the specific heat of the metal, M times C times. Let's look at the change in temperature of the metal. So we're going to do final minus initial, 23.1 minus 99.8. That's a big change in temperature. So negative 77 or 76.7. So again, this metal temperature went down, right? So the delta T of the metal is negative. It started at 99 and it cooled off. The temperature dropped, giving us that negative change in temperature. So we now can just simplify and solve for C, specific heat. Let's do 55 times that negative 76.7. That gives us a negative 4218.5 times C, specific heat. I'm going to leave my Q the same, 1976.94 joules. Now I'm going to divide both sides by negative 4218.5. So 1976.94 divided by that last answer. So the specific heat is, and then our C, what I got was, because we're divided by this negative, because we found that negative delta T, we're actually going to take the absolute value of this because we don't have negative specific heats. That negative is more to imply and tell us that that temperature went down and that our Q, our heat, would be that equal and opposite. So our specific heat with 3 significant figures would be 0.469 joules per gram degree Celsius. And if we were to look at our common specific heats, 0.469, 0.4, that is really close to the standard specific heat of iron, 0.449. So if we did not know what that metal was, we would be able to take a pretty good guess. So we can then figure out our percent error. And to do this, you take your experimental value, which is what we found in the lab, our lab number, and we subtract the theoretical value, which is the published, like what it tells you in the book or what it tells you on a chart. So experimental minus theoretical, take that absolute value, and then divide it by the theoretical value. And times it by 100, because it's percent. So in our case, we would do, okay, what did we get in the lab? We got 0.469 here. What did it tell us on our sheet that the actual was? 0.449. We take that absolute value, divide it by 0.449, and times it by 100%. Let's see what we get here for our percent error. 0.469 minus 0.449 divided by 0.449 and times it by 100. We only got 4.5% error. That's not too bad. Let's look at another practice problem. This one's an ice cube melting one, which is a little tricky. We have two 20-gram ice cubes at -16 degrees, and they're placed into 275 grams of water that's at 25 degrees Celsius. Assuming no energy is transferred to or from the surroundings, calculate the final temperature of the water after all the ice melts. So first, we need to look and say, all right, the ice is going to melt. So if we think about a temperature diagram here, where this is temp, this is time, and this is, let's say this is our -16 degrees. We know that ice, until it hits 0, it's a solid. So let's call this line AB. This is a solid. And then once it hits 0, we know that from B to C here, that it goes through a phase change where it goes from solid to liquid. So we need to look at the energy required to when this ice is going from -16 to 0. So there's a change in temperature. We'll use our Q equals M times C times delta T. But then it also requires energy for this phase change to happen. So we need to do two different parts here. So let's look at line AB. We're going to do our Q equals M times C times delta T. So let's look at our mass. We have 20 grams. And let's look at our specific heat of solid H2O. And notice that it's 37.7 joules per mole Kelvin. And because this is in mole instead of grams, we need to get our grams to moles. And that's just a simple grams to moles using the molar mass. So let's look at this. We have grams of H2O, which is ice here. And we're going to say for every 1 mole of solid water, solid ice, still H2O, I would do 16, 17, 18 grams. And that's just looking at my periodic table and adding together 1 oxygen and 2 hydrogens. So if I do 20 times 1 divided by 18, and actually, shoot, I made a little goof because we have 2 20-gram ice cubes, which means we don't have 20 grams, we have 40 grams. So I'm just going to change this real quick. 40 grams. So here we go. We have 40 grams of water, so let's see how many moles of water we have. 40 times 1 divided by 18 should give me 2.22 moles of solid water. There we go. Okay, now let's plug it into our M times C times delta T. So we have 2.22 moles of H2O times the specific heat, the heat capacity of water, 37.7 joules per mole Kelvin. And let's look at the delta T, the change in temperature from -16 to 0 is a change in temperature of 16 degrees Celsius. And we know that 1 degree Celsius is equal to 1 Kelvin. So we'll just use Kelvin so that our units all cancel out. And if we look at that, we've got moles and moles canceling, Kelvin and Kelvin canceling. So that makes sure that our unit here is in joules. So let's do 2.22 times 37.7 times 16, and our calculator should give us 139.104 joules. Okay, so this is our first Q. We'll call that Q1 or QAB. Now we need to figure out, so this has gotten our ice to the 0 degrees, but now the ice has to melt. So we need to figure out how much energy is required to melt it. So if we look at, this was AB, let's look at BC. And in order to do that, we just need to look at the heat of the fusion. So we're just melting. That's our phase change. So we're going to take our, how much we have. We have 2.22 moles of water. And we're going to look at that enthalpy of fusion, which is 6.01 kilojoules per mole. And if we look, and I just do this, I'm going to have kilojoules, but my Q up above is in joules. So let's just do a kilojoules to joules. You know that 1 kilojoule is 1,000 joules. That'll cancel those out, and I'll have my second Q in joules. That'll tell me how much energy is required to melt my ice all the way to here. So 2.22 times 6.01 times 1,000 should give me, so this is my Q for BC, that should give me 133 for 2.2 joules. So let's add up these two to figure out how much energy is required to melt my ice. So I'm going to do 1339.104 joules plus 133 for 2.2. Let's add these up and I should get 14681.3 joules. And that's required energy. That's the required energy to melt ice. Okay, next. Okay, so this is how much energy is required to melt the ice. Now, remember, we're also cooling off the water. So this is going to be, remember how much heat is required to cool one is warming the other. So this is warming that ice, right? So this energy is the same energy that's cooling the water. So we're going to look at this and go, all right, well, we have the other system is our water starting at 25 degrees Celsius. And that water, so remember, we were warming our ice. We have energy that's used to warm the ice. We also have the opposite energy that is cooling that water down. We don't know what that final temperature is. We need to calculate that, but we're going to use M times C times delta T because there's going to be a change in temperature. It's going to fall, right? We know the mass of the water that we're using. Up here, it told me 275 grams of water. So I know that. I know the specific heat of water up here, heat capacity of liquid water It gives it to me there. And while I don't know, I know the initial temperature, it told me is 25 degrees Celsius. I can find the final temperature because I also know Q. I know right here the energy that's going to be required cooling that water down. So let's plug in what we know. We know our mass. Okay, so we have the mass of our water, which is 275 grams. And if I were to go, okay, mass times specific heat, remember that specific heat here, it's got that mole. So you know what, before we even go, let's change our grams of water, liquid water, to moles of water. And it tells us, or we actually know by adding 1 oxygen and 2 hydrogens, we know that that's 18. We even did that up above. Grams of water for 1 mole of water. So let's do our 275 times 1 divided by 18, and we should get 15.278 moles of water. So let's take this and now plug that in to our m times c times delta T. All right, so we can take our 15.278 moles. The specific heat of water that we just looked up there was 75.3 joules per mole Kelvin. And let's just say we need to find our delta T. We have that initial, we'll plug that in here in just a second. And for our Q, we're going to use this Q. So we're going to plug in our 14681.3 joules. Okay, let's do some combining. 15.278 times 75.3. All right, so these can combine 1150.4334 times delta T. And then to get delta T by itself, let's divide both sides by this. So we're just doing algebra. So 14681.3 divided by that answer. So delta T is equal to 12.7615 degrees Celsius. So I have my change in temperature. And remember, my initial temperature was 25 degrees Celsius. If I had a change in temperature of 12.76, again, remember, my ice is warming up, right? That change in, right now, let's find this earlier page here. My temperature, my ice is warming up. So my water is cooling down. So if I know that I have a change in temperature of 12 degrees and my water is cooling down, I need to then minus 12.7615 to get a final temperature of 12.24 degrees Celsius. Okay, but we're not done because as of right now, we have melted the ice. All right, we have melted the ice. The ice has now become all liquid. The ice is at 0 degrees. We have cooled the water at some point to, let's see, what did we say, 12.24 degrees. So we've gone from 25 to 12 just by adding that ice. So right now our system still is, we still have water from the ice that's at 0 degrees, and we have water that has been cooled from the ice that's at 12 degrees. So now we have one more piece left. This is part 3, where we will have a change in temperature of that 0 degrees warming up from the ice. We will have the change in temperature of what was the water that has already cooled down to 12, but it's going to cool even more. So we have 2 changes in temperature. So we can do one more final piece of warming. What's going to happen? Warm up the, we'll say, melted ice. And we also need to cool down, we'll say, the water even more. So we're going to do our Q and R. We've got 2 Q's here. So we've got an M times C times delta T here, and an M times C times delta T here. So let's take that mass of the ice that we found in moles. We said that was 2.22 moles. So over here, we're going to use 2.22 moles of water. Now at this point, it's no longer ice, it's water, right? We're at 0 degrees, which is water. We've melted it. So we're going to use that specific heat of liquid water, that's 75.3. And that's joules per mole Kelvin. Now we're going to come back to this delta T here in just a second. Let's look at that big glass of water that we have. We calculated how many moles that was, 15.278 moles of water. Specific heat, it's water, so we're using that same 75.3. And, okay, now let's talk delta T. We know the final temperature of my melted ice. We started at 0. So we need to find, it's going to raise. So we're going to take that final temperature, and its initial temperature is 0. So it's going to be a larger number, right? Final minus 0. Remember, we've gone from -16 to 0. We're still at 0 with that ice that's melted. For this guy, we're cooling down. We're at 12.24 degrees, but it's going to warm up, correct? So for this system, it's going to warm up to, I'm sorry, I said warm up. I meant cool down. 12.24, it's going to get even colder because it's got that 0 degree melted ice that's going to warm it up. So we're going to do, since it's going to be a lower number, we'll do 12.24 degrees Celsius minus whatever that final temperature is, because it's going to be lower, right? Here's my higher number, and it's going to cool down to a final temperature. Okay, now we just need to simplify and figure out what that ultimate final temperature is for this whole system. So right off the bat, we have specific heat on both sides that match, so we can just cross that off. That just cancels right out. So I'm going to write this simplified. We're going to say 2.22 moles TF minus 0 equals 15.278 mole 12.24 minus TF. All right, let's distribute both of these. So we're going to have 2.22 TF, and then this will be minus 0, right? So we've got that on the one side, equal to, let's distribute that there and there. So if I multiply that, I should get 187, I believe. Double check to make sure my math is right. Minus, and that'll just be 15.278 TF. All right, so let's get our TFs on the same side. So let's add 15.278 to both sides. So that gets rid of that. So I'm left with 187 is equal to, what is this, 17.498? Now to get my final temperature all by itself, I need to divide both sides. 17.498. And I should get a final temperature of 10.69 degrees Celsius. All right, so to make this happen, we had three pieces to this system. So just going back to recap, we put our 2 ice cubes that were -16. They came out of the freezer. They were below 0. First, we had to melt the ice. So we had to go from -16 to 0 and then melt, do that phase change from solid to liquid. So we had to add energy to melt that ice. And that was 2 parts. We had to do this change in temperature and then the actual process of melting. So we found the energy required to melt the ice. Then we had to look at that change in temperature. When we added the ice cubes into that water, it cooled it some. Thirdly, we then had to cool down the water even more and warm up that melted ice. So our third system was finding what that, after all the ice cube is melted, we have a final temperature in your glass of water. Your beverage is now about 10.7. I guess we should have three sig figs. Yep, this should be 10.7 degrees Celsius when you go to take a drink of water.